Hi guys. So I'm recording some videos covering the ideas from chapter 7 I'd like us to talk about over the next 3 or 4 days. These are the final content from the class. This is going to cover a couple of theorems that are foundational to the way that vector calculus gets used in engineering applications and physics and higher math. So we're going to be talking about is Stokes' theorem and Green's theorem. And Stokes' theorem in particular has some pretty amusing applications that I'd like to show you. It gets used frequently in sort of these kind of higher contexts. And these integrals tend to be difficult to compute, the integrals that we're going to be looking at. So I really want you to focus on the sort of conceptual apparatus of what it is that we're doing. And if I do ask you to compute, I'm going to assign some homework questions to go along with these. We'll talk about what this will look like if it shows up on an exam when I talk to you in class. So I'm going to share my screen here, like usual. So let me turn on my ability, like I said, on both accounts. I can just do this. Share my screen. And I'll open up my notebook. Just here. And we'll start with 7.1. Okay, so the idea here is that, oh, wait a second, let me put this up here. Sorry, somehow I've, I don't really want this to be here. Wait, okay, there we go, that's better. Like a second laggy version of me on the screen. Okay, no, don't need that. I mean, wow. Huh. I haven't had this trouble before. It's like a new feature. There we go. Okay, well, if I can't see myself, then that's fine. I'll just put myself over there. Anyway, now that you've watched me bumble around for a second here, let's talk about parametrized surfaces. So I'm going to start with the idea that's related to the idea of parametrized curves. So remember with the parametrized curve, it is that we had a path, right? So there was some path x of t, and what x of t does is it maps some interval I contained in the real numbers into, say, R3, and where I is an interval of the form AB, and then the path is just some kind of curve floating in space. Now the original interval that we're working with is just an interval that starts at A and ends at B, and what x does is it takes that interval AB and it turns it into some, say, corkscrewing path in R3. And maybe this is x of A, and this is x of B. And so when you parameterize that curve, what you're doing is building a function that lets you travel along that curve in space. And if you recall, we could study the tangent, the sort of slope of this path at a point by looking at x prime of t. So x prime of t is the tangent vector to the curve at the point x of t. So there might be some point x of t, and there's a tangent vector sticking out of it called x prime of t. And so what we want to do is we want to take the same idea, but we want to apply it to surfaces instead of curves. So we're going to lift up one dimension. So I want to be able to do the same kind of thing, but I'm not going to be starting with an interval anymore. I need a two-dimensional set that I can start with for my domain. And now the output isn't going to be a curve, it's going to be a surface. So this is kind of what the beginning of the story is. So we're going to do parametrized surfaces. Okay, so we're going to set up a definition first. So there's some restrictions we need on the sort of sets we can allow for the input to a parametrized surface. We're going to let D be connected, open set, with possibly including the boundary. In R2. And we're going to talk about this set as being D is equal to a set of points that are of the form ST contained in R2. So S is playing the role of the sort of X coordinate and T is the Y coordinate. That's not the same as the X coordinate, Y coordinate. These are playing the role of T in this picture, in the parametrized curve picture. Okay, so a parametrized surface S is a continuous function. X, capital X, so I'll write these to make sure that I'm delineating the capital X's from the small x's. And what X does is it eats the domain D, which is contained in R2, and it spits out a collection of points in R3. And we want this to be one-to-one. Except possibly at the boundary. And so one piece of notation we use is we call X of D the surface parametrized by X. And so we might have called that S as another name for it. And a quick picture of what this looks like, as you can imagine, you start with some set of input variables, S and T, that this is D. And inside here are points S and T. And then we apply the map X to everything in D. And what ends up coming out is this sort of two-dimensional surface bending through space. I want you to imagine here that you get some kind of weird floaty sheet floating around in two-dimensional space. And this is X of D, which is the surface S. And so every point ST over here gets mapped to a point X of ST. And so in the same way that we use little x to describe behaviors of the path in terms of things like tangent lines, we're going to do the same thing with surfaces, where we're going to work with the function big X, and we're going to use that to describe derivatives and tangent planes and whatnot. So first I want to give you some examples of what a parametrized surface is. So here's one. Let's look at X that takes R2, all of R2 into R3, defined by the following function. X of S and T is equal to S times the vector I minus J plus T times the vector I plus 2K plus the vector 3J. So you can rewrite this in the following way. So another way to write this, if you wanted to write it not in component vector form, but in coordinate form, would be to write S plus T, comma, and then what we have in the J component, we have a 3 and a minus S. And in the K component, we have a 2T. And that's another way of parametrizing the surface. And this is two-dimensional because there's two input variables. S and T move independently. And so we expect that the shape that we get out the other side is a surface. In fact, this is easy to see what the surface is. This is a plane. And it's the plane through the point 0, 3, 0, and containing the vectors. Well, the vector we stretch by S, which is the vector 1, minus 1, 0. And the other vector is the vector that we scale by T, which is the vector 1, 0, 2. So this is sort of the way of a parametric way of describing a plane. Okay, so another useful one to take a look at for a second example of a parametrized surface is we could let our domain be equal to the interval from 0 to 2 pi, crossed with 0 to t. When I use this cross notation, 0 to pi, when I use this cross notation, I mean, these are where the s variables are going to live, and this is where the t variables are going to live. And we're going to parametrize the surface in the following way. A surface, rather, in the following way. Let's let x map d into R3 with the following coordinates. So let's let x of s and t be equal to a cosine s sine t, and y of s and t be equal to a sine s sine t, and z of s and t is going to be equal to a cosine t. Now, if you've done any three-dimensional geometry in the past, this should be familiar to you because this is the coordinate transform that gives you spherical coordinates. And it's not difficult to see that what x does to this rectangle. So x starts with this rectangle D, which goes out to 2 pi in the x direction and goes to pi in the y direction. And it has an open end right here because we were only going from 0 up to 2 pi, but not including 2 pi. And so we're taking this region and we're mapping it into this object. Let's start by thinking about what happens to the circle where, say, the s coordinate is equal to 0. Well, what do we get? When the s coordinate is equal to 0, if s is equal to 0, then that means we're looking at the cosine of 0 and the sine of 0. So x of s and t is just equal to a sine t, and y of s and t is equal to 0, and z of s and t is equal to a cosine t. And this is where the t values, so we're looking at this little strip right here. So the t values run from 0 up to pi. Well, it shouldn't be hard to see that this is a half circle. Starting at the point, if you put t equals 0 in here, you get x coordinate 0, z coordinate a. So you start right here. And then when you're at pi over 2, you're at the point a, 0, 0, which means you rotate down here. And then when you're at pi, sine is equal to 0 again, but now cosine is -1, so your z is equal to -a. So this curve right here is the curve that corresponds to s is equal to 0. So there's this fixed curve that turns into this. And in fact, if you sweep through all the angles, what you're going to end up seeing is that this turns out to be a sphere. So the rest of the sphere kind of looks like this. It comes down, it touches here and comes in. It touches back here somewhere, sort of in the back. It touches out here. And you end up with a picture that looks kind of like this. Oh, there's a circle that goes in this direction too. I guess we could put it in here like this. That goes around the edge. And so there you go. This is a parametrization of a sphere in 3 dimensions. And again, the pink line that we drew is on both the sphere and the domain. The pink line in the domain gets mapped by the function x to the pink line in the sphere. And that idea of mapping lines to lines turns out to be really important. So we're going to define something called the coordinate curves. Coordinate curves are a way of figuring out what's going on at a particular point in a parametrized surface. So I'm going to write the definition down, and then hopefully I can make it clear from the pictures what we're doing with this. So let's let S be parametrized by a function x that takes a domain in R2 into R3. If we freeze one of the variables, if we freeze t is equal to t naught, then we get a function of one variable. We get a regular path at this point, because what we can do is we can let the s variable vary. And we get this map where s gets sent to x of s t naught, where again, remember t naught is some constant. Likewise, if we freeze s is equal to s naught, then I could let t vary, and I would get a map that t gets sent to x of s naught t. And these are both paths. Every s naught and t naught that you give me gives me a path, and in one variable. And so what that means is it's a way of looking at lines in the domain and seeing what they do on the surface, just like we did right here. This thing is the path that we got by setting the s variable equal to 0, and then seeing what happens to it once we map through onto the sphere. And then, yeah, so here's a sort of a general picture. If you have some domain that looks like this, so here's a domain D, then you could draw a picture where you set the s variable equal to some constant, s is equal to s naught, and you have a different family of paths, say, where the t variable is equal to some constant, and they intersect at this point right here, which is going to be the point s naught t naught. So s naught t naught is the point where these two paths come together and they cross. And if you look at what that looks like on a surface that's parametrized here, so say you send the domain through x and you get a surface out the other side. So I'll just draw a typical picture of a surface here, or as typical as I can. You can imagine that you get sort of this, like any kind of foldy sheet that's supposed to emphasize here that we're looking at a surface sitting in R3. Then the blue curve, if we look at the point s naught t naught, that point s naught t naught is going to get mapped somewhere on the surface. So right there is the point x of s naught t naught. And running through that point are the paths that you get by taking the blue line and shoving them through x, and then taking the pink line and shoving them through x. And so you might get a line that looks like this. This is x of s t naught. It's the coordinate curve that you get by holding t naught constant. And in the other direction, you have the coordinate curve that you get by holding s is equal to s naught constant, which maybe comes in like this and goes through, and then up here. So this is x of s naught t. And the reason that we do this is because these curves tell us at a point on a surface, they actually give us a way to calculate derivatives. We could calculate a tangent plane if we wanted to from here, or a normal vector. Like that's kind of what the goal of these coordinate planes is to give us an idea of like how we can compute a derivative. And then once we have the derivative, we could use it to put a tangent plane together. So I'll give you one more quick example here of a tangent plane and, or sorry, of coordinate curves. So here's a concrete example that you can think about. So imagine that you have x of s and t is equal to a plus b cosine t. Sorry, that's not quite right. A plus b cosine t cosine s, comma, a plus b cosine, no, once again, go, cosine t sine s, comma, b sine t. And here, our domain is given by 0 to pi cross 0 to pi. Remember, these are the s variables and these are the t variables. So this time, I'm just going to draw this for you. You can put this in Math 3D if you want, or you could work this out by hand. This turns out to be a torus, so a donut shape. So you've got this rectangle that runs from 2 pi in both directions. And if you run this through x, what you end up with is a torus that has an outer radius of a plus b and sort of like an inner radius of b. So you get this sort of figure out the other side. I will do my best here. So you get kind of this donut shape. And then you can imagine that behind here, there's the hole. And then it kind of comes in front, it goes like this. So there's a torus. And if we drew curves through the domain that we've set up, the lines that cut through this way give us curves that run lengthwise around the donut. And if we have curves that go the other way, let's move this here. If we look at the other coordinate curves, that gives us circles that look like this. They run around the torus this way. And so these curves all together, they build up the torus. And so this is worth taking a look at, seeing if you can, so this is an example in the textbook. It's a nice example. You can walk through the computation. But the idea is if you fix one of the variables, the other one corresponds to shapes that look like this. Again, this is sort of high level way of thinking about how surfaces are built up. Now, the point is that if I want to know what the normal vector is to this curve, I mean, ultimately what we want to do is we want to describe it with vectors. And tangent planes and normal vectors are sort of deeply connected with each other. And so what these coordinate curves are going to let us do is actually get a definition of normal vectors. So we have to make one additional assumption first, which is that everything here is differentiable. So what we want to do, so we want to use the coordinate curves at a point to compute tangent vectors. And ultimately, if possible, normal vectors. Because if I have a normal vector, I could compute things like interaction between a surface and a vector field. So if X is C1 at every point in D, then we call S, remember which is X of D, a differentiable surface. And that means we can define two new vectors. So we're going to define the tangent vector in the S direction at S naught T naught to be equal to dx ds at S naught T naught I plus dy ds S naught T naught j plus dz ds S naught T naught k. So in the picture up here, the derivative in the S direction means we're traveling along a pink line, which would mean that you can think that at this point right here, you get a tangent vector that kind of pokes out like this. So that is the vector that we're going to call TS at S naught T naught. It's a tangent vector that runs along the pink curve, right? Which is a curve where the S variable is changing, but the T variable is fixed. And then we also have TT at S naught T naught, which is just the derivative with respect to the other variable. Dx dt S naught T naught I plus ds dt S naught T naught j plus dz dt, it's supposed to be dy dt. Dy dt and dz dt at S naught T naught in the k direction. Okay. And on the picture that we drew before, that vector points in the direction the blue curve is moving, which means we look like this. So this is TT of S naught T naught. So those tangent vectors give us a way of sort of, again, describing the behavior of the surface at that point. And what we'd really like to do with this is to use it to define the unit normal vector, because the unit normal vector tells us exactly how a surface is changing as we travel along it. The unit vector tracks the way that the surface is curving, and it turns out to be the case that the length of the normal vector carries important information as well about how the parametrization is taking little areas in the domain and transporting them into little rectangles in the surface. So we got one step higher than differentiable. So the final definition we need here is we're going to say a parametrized surface is smooth if at every point x of s naught t naught, the normal vector n of s naught t naught, which is equal to the cross product of ts s naught t naught and tt s naught t naught, is not equal to the zero vector. So this is going to basically tell us that the normal vector never disappears. The normal vector disappearing would say that somehow the surface like flattened out in some kind of strange way, and we don't want that. Yeah, and so this thing n, which is ts cross tt, is called the standard normal vector. And the picture here is you have some surface, you have a point, which is x of s naught t naught. Through that, you have coordinate curves, which look like this. You calculate derivatives along both of those curves, and you get these arrows. So in this direction, you get ts, and in this direction, you get tt. Take their cross product, and you end up with a vector that comes perpendicularly out of the surface called n. And I guess I should be careful here and put hat notation on these guys, so that we're completely unambiguous about the fact that we're talking about vectors here. Okay, so that's a really important thing to be able to do. And the reason that's important is because this is going to give us automatically a notion of how to find the surface area of a parametrized surface. So we spent some time talking about how to keep track of the distortions of areas as we move from one set to another. This is kind of related. It turns out to be the case that the way to keep track of the surface area of a surface is as follows. So if you start with some domain D, here's D, a domain, and you keep track of a little rectangle on the inside here, and this rectangle is going to be ds by dt. So it's a little square, it's ds by dt wide. And you take your domain and you map it over with x. So x is the parameterization that builds the surface. And you look at what happens on the surface. Well, where does this little rectangle end up? Well, it's going to get mapped to some shape over here on the surface. And it turns out to be the case that that shape can be approximated by the tangent vectors. So we have this vector that pokes out here called ts, and a vector that points this direction called tt. And so the area of this parallelogram is part of the surface area of the whole surface. So what I want to do is I'm going to slide my little ds dt all around the domain. And when I do that, I'm going to get all these little parallelograms over here in the surface that approximate the surface area of the whole thing. I want to add them all up. Well, the way that you do this is with a cross product. It turns out that the area of a parallelogram is equal to the cross product of two vectors that define it. We talked about this a long time ago. And so you define the surface area of some parameterized surface x of d with a double integral over the domain, where you take all those little dsdt's and you slide them over into the plane. The length of the vector in one direction is ts ds dt, and it's ct tt dt in the other direction. So what do? You calculate the cross product. This thing right here is the area of the little parallelogram. And of course, you can make this a simpler formula by writing this down. And that's it. That's the definition of surface area here. So surface area of a parametrized surface is picked up either by thinking about it being broken into little parallelograms that are approximated with these tangent vectors arising from the coordinate curves, or you could think about it as the length of these normal vectors, because that's what a normal vector encodes. A normal vector encodes the length of some parallelogram that it arises or is normal to. Okay, so again, that's sort of our core idea here, is that when we're looking at parametrized surfaces and we want to chop them up into little pieces and then investigate what's going on the surface in little pieces, our basic idea is that the unit that looks like this is a measure of unit area. Okay. And in fact, this bad boy right here is usually called ds. We'll see this again. All right. Now, I mean, maybe I won't cut it off quite yet with the all right. It looks weird to write it that way, but remember that when we learn length, right, that the length of a curve is just f ds. It's exactly the same thing that we're doing here. Okay. All right. Well, I'll see you for the next one. Practice these. They're cool. This is good stuff. And I'll talk to you about 17 next time.